Hello and welcome to sections 10.1. So all of chapter 10 we're going to look at three-dimensional space. Okay, traditionally we've often looked in 2D space. We've had y as a function of x, or maybe x as a function of y. We're basically going to add an extra variable. Okay, so let's go ahead and see what that looks like. Okay, so I'll say quick reminder of what 2D looks like, and we're all very familiar with this. If we have a point, a Cartesian coordinate in 2D space, we're very familiar that if we see that 3, 2, that means we go 3 in the x direction and 2 in the y direction. And we've seen that so often, we're kind of familiar with that, and that's very straightforward. Now we're going to look at points in 3D space. Okay, so before we actually look at that point, let's just notice something about the axes. So we have an x-axis, a y-axis, and then up from that is the z-axis. The z is going positive in that upward direction, and there's a few ways of remembering that. One is just to look at this picture. The right hand rule, if you sort of curve your hand round and your fingers are pointing going from the x to the y, your thumb pointing upwards would be the z. Another way to think about it, if you draw an x and y axes as you normally would on a board, the positive z would be coming out at you to kind of poke you in the eye. Okay, and then we have that p there, right? So we have that point. And whereas before we had a point with 2 variables, now it's going to have 3. Okay, so again, it's going to be the x and the y and the z. So here the x value is 2, the y value is 1, and the z value is 3. It's always a little hard to see in these 2D pictures, but hopefully you can see how that point P in the picture there goes along 2 in the x direction, goes along, 1 in the y direction, then up 3 in the z direction. So that's how we think of a point in 3D. Now, of course, we can make it look different, right? This is exactly the same point. We've just written the x and the y and the z axis a different way, but it is that same 2, 1, 3 point. I think traditionally we'd probably write the axes as we have on the left there, but that's not to say the one on the right is wrong. Okay, so how about distances? Okay, so if we have a point in 2D space, we want to find the distance from the origin. We sort of are familiar with Pythagoras. So we take the square root of 3 squared plus 2 squared. So if we do something very similar, yeah, there it is. If we do something similar in 3 dimensions, so we want the distance between 2 points in 3 dimensions, we just take the difference between the x values, square it, the difference between the y values, square it, the difference between the z values, and square it, and take the square root of all of that. So it's really just an extension of the Pythagorean theorem to 3 dimensions. So let's take a quick example. So we have 2 points, q is 2, 1, 1, and p is 1, 4, -1. We want to find the distance between those two, and here they are on a graph. Hopefully that makes sense. So again, we have those axes, the x and the y, and then the z going up. And you can see the p there is below sort of the level plane because the z value is -1. So we want to find the distance between those. So we take the 1 minus 2, so that's the difference in the x values. And keep in mind, because we're going to square it, it doesn't actually matter if we do 1 minus 2 or 2 minus 1. 4 minus 1, and then minus 1 minus 1. Square each of those, add them together, and take the square root. So the distance between those 2 points is the square root of 14. Okay, so just like we have 2D shapes, we can have 3D shapes. So again, looking back at something in 2D, kind of familiar, hopefully, with a circle in 2 dimensions. We sometimes write it as y equals the square root of, but the more general form is this. So we have x squared plus y squared equals r squared, or x minus a squared plus y minus b squared equals r squared. So this would be a circle of radius r centered at AB. Okay, well, similarly, if we want to look at a sphere in 3D, and you can see how it's very similar. So we've got x minus a squared, y minus b squared, z minus c squared equals r squared. So this would be a sphere rather than a circle because it's a 3D shape. It's going to be centered at ABC, and it's going to have a radius of r. Okay, so that's a first example of a 3D shape. Okay, we have an x, y, and a z coordinate. Okay, so let's try and find the center and radius of a sphere. Okay, so first, how do we identify that, well, in fact, this really is a sphere? So we have the x squared, y squared, and the z squared, and we have some sort of constant terms of x and y and z there, and that all equals a constant. But it's not really in the form we want, right? It doesn't look like this. So to make it look like this, we're going to have to complete the square in each case, for the x and the y and the z. Okay, so completing the square, let's just think about the x. So we have x squared plus 2x. Well, what completes the square of x squared plus 2x? Well, that would be x squared plus 2x plus 1. Similarly, for the y, we probably get a minus 2, I think. And for the z, a minus 3. So let's go ahead and look at that, right? So we have the x squared plus 2x plus 1, y squared minus 4y plus 4, and the z squared minus 6z plus 9. But in completing each of those squares, we've added a 1, a 4, and a 9, so a total of 14. So we also have to subtract 14 there, so that's why we get the minus 14 at the end. And it still equals that 2 on the right-hand side. But now we have this in exactly the form we want, so each of the terms in the parentheses there, we can just factor. So the first one will be x plus 1 squared, then y minus 2 squared, and z minus 3 squared. We take the 14 over to the right-hand side to make 16, and I think that's all we need. So there it is, x plus 1 squared plus y minus 2 squared plus z minus 3 squared equals 16. So this would be centered at negative 1, 2, 3, and it would have a radius of 4. There it is. Okay, so that's a way we can take something that isn't quite in the form we wanted and create the form we do want. It tells us it's a sphere, and in fact where it is, and indeed how big it is too. Okay, so that's a simple shape. Looking at other simple shapes, so obviously a plane is a very simple shape in 3D. So just like we have a line in 2D, we can have a plane in 3D. So this is the XY plane, right? You can see it's flat on the X and the Y axis. But another way of thinking about this plane, it's the plane Z equals 0. Okay, you think about all the different points where Z equals 0. Well, if Z equals 0, X and Y can be whatever they want. So Z equals 0 would just be that flat plane right there. Similarly, we can find the YZ plane. So this is all the points where X equals 0. And we can find the XZ plane, that's all the points where Y equals 0. So those are our three sort of standard planes. Because we're not restricted to those, we can have any other plane. If we take the plane X equals 2, that is a plane where all the X values are 2, and again Y and Z can be whatever they want. So it's parallel to the YZ plane, but shifted, you can see, towards us and to the left 2 points. And of course you can also have angled planes, but for right now these are the very simple standard planes we can have. Okay, and then one more shape we're going to look at is cylinders. So we kind of have a sense of a cylinder in real life, right? A soda can we think of as a cylinder. The definition in math is a bit broader than that, and the picture will help us a little bit. So here's the definition. Let C be a curve in a plane, let L be a line not parallel to C, but then a cylinder is all the lines parallel to L that pass through C. And really how we should think about it is all those parallel lines L. So let's consider taking a bunch of circles. Right, so if we take a bunch of circles all parallel to each other, and this is just 3 of them, but if we have infinitely many of those, so I guess this is the circle, what is that, x squared plus y squared equals 1, it looks like, right, so just a circle. But again, Z can be anything, so we take these 3, but if we keep building with more and more of these circles, well, eventually we get a full whole cylinder. Okay, so if we take x squared plus y squared equals 1, but don't specify z, z can be any value, so we get all these parallel lines that create a cylinder. But I'd say that's actually just one example of a cylinder in 3D. It doesn't have to be a circle shape that creates a cylinder that we think of like a soda can. So for example, let's take z equals y squared. So again, it's a function of z in terms of y, but we don't specify x, which means x can take on any value. So if we look at A there, well, that's the simple version of z equals y squared, right? It's a parabola. We're fairly familiar with that shape. It's going upward there as the z goes. But now we're going to take all the things parallel. So as B suggests, we can take all these lines that are parallel to each other and then go along that y equals z squared, and that creates that big kind of, I guess, almost like a skate park curve thing on C there. Okay, and although it stops, actually this would go infinitely far in the positive and negative x direction. Okay, and then the last one, if we take, let's take x equals z squared. So now x is a function of z, So it creates that standard sine curve that we know. Then because we don't specify y can be any value, so we can extend kind of back and left and forward right. And so we get that kind of 3D sine curve on the right-hand side there. And I say that all of those are cylinders in 3D, even though, we don't really think of them as standard cylinders. Okay, so that's it for the introduction to 3D shapes. Thank you.